Have you tried to design a control law for a time delay system in the presence of perturbations without the knowledge of their upper bound? The presence of the delay in the system dynamics poses an interesting challenge when attempting to apply classical robust control approaches typically used for pre-delay systems. In cases where the upper bound of the perturbation is unknown, adapting the controller's gain becomes necessary to effectively handle variations in perturbations, even in the presence of delay. In this talk, we'll give an adaptive control law for the uncertain time delay system at the joint of the classical problem of Lyapunov redesign and the quite recent approach of varied function-based sliding mode control. My name is Christopher Cruz-Ancona, and it is a pleasure for me to present our work entitled Adaptive Lyapunov redesign for a class of linear systems with delays in the state. This is a joint work with professors Marco Gomez at Universidad de Guanajuato and Leonid Friedman at UNAM in Mexico. Let me start first with an introduction on the so-called Lyapunov redesign. Lyapunov redesign refers to a constructive approach to control perturb systems based on Lyapunov functionals. Its roots date back to the work done by Professors Lehman and Gutmann in the late 70s in the framework of free delay systems and Lyapunov functions. Since then, it has been widely applied as a standard robust control approach. In the context of time delay systems, the pioneer extensions were developed by Towson in the early 80s by using Lyapunov-Razumikhin functions. Later on, this approach was extended for Lyapunov-Krasovsky functionals during the mid-90s with some emphasis to slide mode control. The idea is to reuse the Lyapunov-Krasovsky functional of the nominal system, but now in the presence of uncertainties. This allows us to redesign the control law from the time derivative of the functional. However, two disadvantages are clear in this approach. The redesigned law is based on unit control, which is discontinuous and causes the undesirable chattering effect. Also, even for continuous approximations of unit control, the control gain should be chosen greater than the upper bound of uncertainty, which is unknown in principle or overestimated. Since the perturbations are known, there is no chance to compensate them and achieve asymptotic stabilization without overestimation of the controller's gain. Instead, and to overcome the above disadvantages, we rely on the adaptation of the unit control gain. The following are the main features of the present approach. The ultimate bound of the solution is determined without a priori knowledge of the upper bound of uncertainty, regardless of the presence of delay. This is achieved by ensuring a predefined reaching phase in a predefined time despite the delay. The norm of the sliding variable attains a value lower than epsilon in a finite time bar t. This finite time is upper bounded by the sum of predefined time PR and the value of the delay. This means that the solution uniformly reaches a neighborhood of the sliding set and never leaves it. And then, after a finite time, the solution of the time delay system will be contained in a prescribed in advance neighborhood of the origin for all future time. Another feature is that the gain adaptation to the sliding phase produces a continuous control signal adjusting the chattering. Let's shortly revisit the Lyapunov redesign in the eyes of sliding mode control and then introduce an adaptive based solution. Consider the following time delay system where x and u denote the state and input. H represents the known value of the delay. T represents the input matrix, which is continuous in T and Lipschitz in X. Assume that there exists a stabilizing control UN of T and a nominal continuous differentiable Lyapunov-Krasovsky functional B, satisfying the asymptotic stability condition. This condition means that the origin of a closed-loop nominal system is asymptotically stable, AS, in the supremum norm. The class of the Lyapunov-Krasovsky functionals is that given by the sum of a function independent of the delay B0 and a functional given by the integral term. An example of a functional in this class is found in sigma stability results, for instance. Now, what changes to ensure the asymptotic stability condition when the time delay system is uncertain? The system is now perturbed with the uncertain control matrix uppercase delta G and a matched perturbation term lowercase delta. Consider the input of the system as the sum of the nominal control law and a reverse-defined control law UR. We assume that the uncertainties and perturbations are bounded, but the upper bounds are unknown. Moreover, the uncertain control matrix satisfies the control limiter condition that ensures that the control matrix can reduce the control effort when this condition is positive. Consider the nominal Lyapunov-Krasovsky functional attains this derivative along the trajectories of the uncertain system. One cannot conclude anything from the sign of the terms in the right-hand side of this inequality. The first term is due to the asymptotic stability behavior of the nominal closed-loop system, which is negative. However, the second term, which contains the perturbation, is sign indefinite. Let us define the memory sliding variable sigma transpose as the gradient of B0 times capital G, and designed the robust-defined control law UR to compensate the uncertainty in the derivative of the Lyapunov-Krasovsky function. Particularly, design UR to restrict the solution of the closed-loop system, which is on a piece of trajectory restricted to the interval t minus h to t, to the manifold S in a finite time bar t. If this is achieved, the signed indefinite term in the upper bound of B dot becomes zero. Hence, B is still a Lyapunov-Krasovsky function for a uncertain system, and asymptotic stability is recovered. It is worth mentioning that under this approach, the design of the sliding variable is not needed anymore, and a standard first-order sliding mode control design can be done. The sliding mode control design requires to synthesize the controller UR for the relative degree 1 sliding dynamics with matched perturbation. The following assumptions are needed. It is required that the relative degree is well defined, or equivalently that the matrix G0 in the sliding dynamics is non-singular. This is standard. Also, is assumed an additional restriction on the uncertain control matrix. This additional restriction is required to relate the size of the state of the system in terms of the sliding variable within the time derivative of the Lyapunov-Krasovsky function. The solution of the time delay system in closed loop with the nominal control and robust control is entirely restricted to the manifold S within a finite time and stays therein for all future times. Clearly, this is achieved if the robust-defined control law is selected as the unit control, and the unit control gain is equal or greater than the upper bound of uncertainty. This approach has three clear disadvantages. The finite time to restrict the solution to the manifold S grows unbounded with the delay, upper bound of perturbations, and the initial condition. The control law is discontinuous, which produces the undesirable chattering effect, and moreover, the upper bound of the perturbation is unknown. To deal with these issues, the adaptation of the unit control A can be proposed at the cost of losing asymptotic stability of the closed-loop system. A sharp adaptive solution should solve the following problems. Problem 1 is to give a uniform adaptive reaching phase. The adaptive unit control should ensure a convergence to a neighborhood of the sliding set in a finite time with a predefined upper bound despite the delay, the perturbations, and initial conditions. Problem 2 needs to give an adaptive sliding phase where the unit control gain should follow the perturbation variations without being overestimated, and to give a predefined phase where the system trajectories are ensured to enter into a priori predefined vicinity of the origin and never leave it despite the perturbations. Our solution is to combine the uniform adaptive reaching phase strategy and the variable function-based adaptive Lyapunov redesign. For given the adaptive controller, let's restrict our attention to the class of perturbations without a priori bound. This class considers all perturbations with unknown upper bound that, particularly, the perturbation upper bound rho 0 is said to be partially known if it can be written as the product of a known positive constant and a partially known function capital gamma. Capital gamma depends on a known manner or a vector of uncertain parameters as shown in the slide. This assumption is commonly accepted in adaptive control. Consider again the sliding dynamics put down in the closed loop with a unit control law and with control gain that is adaptive. The adaptive unit control gain switches once between two different gains. The first gain is composed of three terms with different adaptive rules to ensure a uniform adaptive reaching phase. The first rule, capital T, is an increasing term that becomes unbounded at the time capital TR. The second rule tries to estimate the unknown vector of parameters of the perturbation upper bound, and the third one adjusts a rapid convergence if TR is chosen very large. The second gain is a positive semi-definite variant function that guarantees an adaptive sliding phase with a real sliding mode of size epsilon. The time TR that indicates the end of the reaching phase and the size of the real sliding mode epsilon are predefined by the user. How does the adaptation work? Intuitively, we can think as follows. Consider the norm of the sliding variable, the norm of the perturbation, and the adaptive gain in the plot on the right-hand side. The features of the adaptive gain can be described intuitively by looking at the behavior of the sliding mode dynamics during the reaching phase and the sliding phase. At the beginning, the gain increases to a value confining the norm of the sliding variable to a value lower than epsilon in a finite time bar t, despite the size of the norm of the perturbation. Hence, the system solution reaches a neighborhood sliding set for the first time. This finite time is upper-bounded by the sum of the predefined time tr and the value of the delay. Therefore, it is possible to know beforehand when the reaching phase ends. After the system solution reaches the neighborhood of sliding state, the gain is switched to a positive and negative variable function. The adaptive sliding phase starts. The solution follows stable sliding dynamics, where the gain follows perturbation variations without overestimation for all future time, while the norm of the sliding variable remains uniformly bounded by epsilon. In summary, it can be ensured that the sliding variable accepts a lower and upper bound depending on epsilon, which can be used to predefine a bound for the system solution. Moreover, the adaptation adjusts the chattering by removing the discontinuity from zero in the unit control law. At the moment, we can think in our solution as the design of UR to restrict the sliding variable to a predefined epsilon neighborhood of the sliding set. However, let's return to our original problem. How it is possible to prescribe an ultimate bound for the solution of the time delay system? This can be done by following the next steps. For a sufficiently large bound R of the solution of the system, the restriction on the neighborhood of the sliding set imposes the following upper bound for the time derivative of the Lyapunov function. It is clear that one can recover the negative sign of the derivative of b if mu is chosen as indicated. Notice that mu depends on the predefined parameter epsilon. From the negative sign of the time derivative, it can be provided that the function attains the value of its upper bound evaluated at mu at the finite time capital C. From classical Lyapunov arguments, it can be seen that the present state is ultimately bounded with bound capital R. Then one can choose epsilon in terms of any prescribed value of R. Finally, we can conclude the following. Given epsilon and the predefined time Tr, the closed-loop solutions of the certain time delay system fulfill that the uniformly bounded set of the sliding variable will be reached in finite time. Moreover, the trajectories of the uncertain system will be ultimately bounded with a prescribed ultimate bound b of epsilon, where b is a prescribed class K function. To illustrate our adaptive solution, consider the academic example taken from the reference below with the following system parameters. Further details can be consulted in the conference proceedings. To show the advantages of the proposed adaptive approach, a comparison with the unit control law and the supertwisting algorithm involved with fixed gains is made with the same sliding variable as indicated below. To test the adaptation in the unit control gain, the perturbation delta contains a non-vanishing sinusoidal function eta that increases and decreases its amplitude over time. The results for numerical simulations are given next. This picture shows the norm of the solution in 80 seconds of simulation time. The curves represent the simulation scenario with different controllers. In the top figure, we can see that the norm of the solution in each case attains a vicinity of the origin. However, the difference resides in the amplitude when the perturbation derivatively grows. In the bottom, a closer look of the last 35 seconds is shown. In our approach, represented by the green curve, we see oscillations with decreasing amplitude in the same fashion as in certain term. However, in the cases of the unit control law and the supertwisting algorithm, the amplitude cannot be maintained because of the gain in these controllers is fixed. The behavior is more evident if we look at the norm of the sliding variable. This figure illustrates the same three scenarios. Our solution ensures that the norm of the sliding variable is contained in a prescribed vicinity of zero that will never be exceeded. On the contrary, for the other two controllers, we can see that the auxiliary variable cannot be maintained with the same prescribed neighborhood. Finally, the following picture depicts the control signals in each scenario. In our approach, we see that the control follows the changes in the amplitude of the perturbation in a similar fashion as the supertwisting algorithm. In the case of the unit control, we see that the control signal chatters when the gain overestimates the size of the perturbation. As final remarks, we would like to point out the following. In this work, we propose an adaptive control law that ensures that the solution of the certain time delay system will converge to a prescribed set. This is obtained without the knowledge of the upper bound of uncertainty and independently of the delay. A predefined reaching phase ensures that the solution of the certain system will be contained inside the neighborhood of the sliding set in a finite time that can be a priori bounded. If the solution converges to the prescribed set, the adaptive gain will follow perturbation variations. This means that the energy consumption for the equator will be diminished. For coming work, we'll include comparisons between this approach and other methodologies in adaptive control of time delay systems. So now you have a control designed for a time delay system in the presence of perturbation without the knowledge of their upper bound. Thanks for watching. See you next time.